Welcome to the second day of our AIDS workshop. Today we are going to talk about mostly neural networks. Our focus would be on neural networks followed by convolution neural networks and then creating different components of a convolution neural network with a DenseNet one-to-one application. So think about it for a second. How do you know that this is a cat? Like, how do you know our brain is working? You weren't born knowing. Your brain learned from seeing many examples. We were told that this is a cat from our childhood, and that's how I know that this is a cat. However big or small the cat is, our brain is functioned to analyze that this is a cat. A neural network is similarly programmed as a computer system inspired by your brain design to do the same thing, learn patterns from the data. So what is the main goal of neural network? What do you think is the main goal? To store data like a hard drive, to learn patterns from data, or to run computers programs faster? Well, to learn patterns from data, right? That's very simple. So what if the network guesses dog, but the image is cat? So what happens in that situation? So if think of it for a moment. If we are guessing something wrong, then we are being told that no, this is wrong, and that's kind of a penalty that's happening for us. Right? The difference between the guess and the right answer is also called loss or error. So we are being told that this is an error, and the network is also being told that this is a loss or an error. The network then uses backpropagation. So it propagates back, it works backward from the error to see which connections were most responsible for the mistake and adjust them accordingly. It's like a coach giving feedback to a player to improve their next shot. Okay. Okay. So the network gets dog, but the picture was cat. What should happen now? Nothing. The network tries the new image. The network uses backpropagation to adjust itself. The input image is deleted. So it's again B, right? Because we would ask the network to guess it again and train itself better by backpropagating and adjusting itself. The special networks are seen. So the convolution neural networks were the special networks that can see images. Okay. So the computer sees an image as a read of number. A regular neural network gets confused by this. A convolution neural network is a specialist for image. If it uses filters to scan an image and looks for specific features like edge, corners, texture, and shape. So how do you know this is a cat? We would look at its head, then its body, then its shape, and that's how we know it's a cat. And similarly, this is done by filters. So this is our image. The red, green, and blue are three channels of an image, and this is our filter. So it moves to the filter, it does a dot product conversion or matrix multiplication, and it creates a output of size 3 by 3 for all the red, green, and blue channels. So spot the feature. If a CNN filter is looking for circles, click where it would get the strongest signal on this card. So it's looking for a circle, right? So it's this one, right? So it's mostly like a circular shape, right? So this is the pattern it's looking for. It's looking for a circular shape, that is the C. Okay, so how do you think it's trying to make the predictions? So the flow of information, so it's doing a forward propagation. In the process of data moving to the network from input to output, the network takes your input data, passes it through hidden layers, and makes its best guess or prediction. The neurons math. So how do you do a neurons math? So it's a simple calculation, sum of all the inputs multiplied by their weights, then add a bias. So W1, X1, W2, X2 plus the bias. So Z equals to W1, X1, W2, X2, whatever all the weights are coming from, sum it up and then add the bias. Okay. So what is the primary purpose of forward propagation? It doesn't learn from mistakes, right? It's just making a prediction to generate a prediction from an input image. So if you have this input x1, w1, x2, w2, and a bias 0.1, then how do you calculate the bias? So just add sum up w1, x1, w2, x2 plus the bias and then put an activation. So activation, we'll talk about it, is basically making your neural network have some non-linearity. So if we calculate what is the z value for neuron, so w1 x1, w2 x2 plus the bias. So basically that will sum up to, let me draw this. So w1 x1 plus bias. So 3 into 0.2 plus 1 into 0.4 minus maybe plus 0.1. That goes to 0.6 plus 0.4 and 0.1, actually 1.1. So that's the value of your C, right? Okay. So building blocks and making a guess. So the neural network is made up of layers. So it has input layer, hidden layer, and output layer. Where the data enters is the input layer, the brain where the features are detected and processed and gives the final answer as cat or dog is the output. When data moves from input to output to make a guess, it's called forward propagation. Fixing the mistake. After guessing, the network compares its prediction to actual answers. The difference is the loss or error. Backward propagation. Sends this error signal backward to a network to figure out which weights and biases are most responsible. It then updates them to do a better job next time. So new weight equals to old weight minus learning weight into gradient. So the gradient is just the direction of blame for the error. Okay, so which way is the gradient passing? If the gradient passes right, then we get a better weight. If it's wrong, then we get a wrong weight. What is the main goal of backpropagation? Calculate the error and update the weight. Yeah, calculate the error and make and update the weight. Okay. Gradient descent. So this is very important. The process of minimizing loss is called gradient descent. So think of this like this. So the hill is the loss function. The bottom of the hill is the lowest possible layer. The steepness is the gradient, tells you which way you can go. And there's a step size, which is called the learning width. So the steepness of the gradient, you can take any weight, which is any directional weight, which will give you a better width value. Right? And the step size can be small or big depending on how steep the gradient is. The backpropagation finds the gradient and the gradient descent takes the step. So the hill, what is the hill? It's the loss function. Step size is the learning rate and stiffness is the gradient, right? What is padding? Now we will go into different elements of the CNN. So what is padding? In a CNN, padding is the process of adding extra pixels, usually with a value of 0 around the border of an input image or feature map. Why is it important? So it preserves the spatial size. Without padding, the output feature map would be smaller than the input size. So sometimes when you do it with kernel, as you saw earlier, that a bigger picture actually converted into a smaller picture, and padding helps maintain this direction. Improves border processing. It allows the convolutional filter kernel to process the pixel at the borders of the image more efficiently and multiple times. Right? So If you stop at the border, it might not get those pixel values at the border. So that's the reason it's kit and padding. So let's look at padding. Okay. So this is the input size. You have a kernel size of 3, and then you get a output size 5 by 5. See, the size is preserved. Okay, which if you have a padding. So this is the actual image, and the size over here is then preserved. But if you have no padding, just one layer, so its size becomes 3 cross 3, and that will be a problem, and because it downsizes the image. So stride is the number of pixels the convolutional filter moves over the input matrix at a time. A stride of 1 means that the filter moves 1 pixel at a time, and stride of 2 means that it moves 2 pixels at a time. So how does it control? Controls output size. The larger size results in the smaller output feature map. This is because the filter takes fewer steps to convert the entire input. Using a stride greater than 1 is a way to downsample the feature size, reducing its dimensions and computational cost. So this is a filter. If it moves one stride at a time, so 5 by 5 and 3 cross 3 is the kernel size, output is 3 cross 3. If it moves by 2 strides, then output reduces further, 2 cross 2. Okay. So finally, let's go into activation function. I made a mistake. So we'll go over here, pooling layer first. The pooling layer shrinks the feature map. It has two main benefits. It reduces the amount of computational data for the network, and it makes the detected features more robust to the position in the image. So this is the image, and we are breaking it down into 2 cross 2. Okay, so I'm taking the maximum 8, 7, 9, and 5. The most common type is max pooling, which takes the maximum value from a smaller window. And then we have a flattering layer. The convolution and pooling layer are great to find features, but their output is a 2D grid or multiple grids. The next stage, the fully connected layer, is a standard neural network that expects a simple one-dimensional list of vectors. The flattened layer only job is to unroll the 2D grid into a 1D vector. So see, it has a 2 cross 2, and then it's just flattening it out. All the values are just flattening into one row vector. Right? So then a fully connected layer. This is a classic artificial. It takes long vectors of features and learns which combination of feature corresponds to which. The final layer is a softmax, which is basically giving a probability, right? Outputs a probability for each possible case. The class with the highest probability is the new network's prediction. If the output for cat, dog, and classifier is 0.92 and 0.08, what is the network's prediction? A 92% chance it's a cat. And 8% chance it's a cat, it's 92% chance it's a cat, right? Then this is 8% chance it's could be a dog, right? So that's what it means with the probability sizes. Now let's talk about the activation. So what is an activation function? An activation function acts like a switch or a gate for each neuron. It takes the output signal from the previous neuron and converts it into a form that can be passed to the next neuron. They introduces non-linearity into the network. Without them, a neural network, no matter how many layers it will have, it will just learn nothing because it's a linear model. This non-linearity allows the network to learn complex patterns and relationships in the data. Okay, so here is the neural network. So if there is a certain value, it remains 0, otherwise it's just a linear way. So it provided some very fast and efficient and makes the most popular choice for hidden layers. So it's very important for activation. So let's bring it all together. A CNN processes an image in a series of specialized stages to arrive at a final prediction. Each stage has a specific job: input, conv plus value pooling, sorry, yeah, pooling which downsamples it, flattens it to 1D, and then fully classifies the network. This sequence of feature extraction followed by classification is the core of how CNN works. So let's look at the math behind the magic. So the convolutional layers applies a filter across the input image to create a feature map. The output size depends on stride and padding. So input summation of input star across filters plus bias, right? So X plus W plus bias. That's basically it. Reduce the size of the feature map, keeping the most important information. Max pooling is most common. Output XY equals to max of the region, right? And the fully connected activation, which plus input plus bias, kind of it gives you the probability. So activation gives you those probability values. So as a final check, after the convolution and the pooling layers have extracted the key features like edge, textures, and shape, the data is still 2D grid format. However, a standard fully connected layer needs a simple flat list of numbers, a 1D vector as an input. A special simple step is needed to bridge the gap. Which layer is responsible for converting the 2D feature mapping to 1D vector? The pooling layer, the convolutional layer, flattened layer, or the output layer. So it's the flattened layer because it's converting the 2D feature map to 1D vector. Now we will look into a Google Colab notebook.